Today we're going to meet Mondriaan, not the painter, but the sparse matrix distribution. This is the matrix imcol from Imperial College, which represents a chemical reactor. We have split it in a Cartesian way, first by a vertical cut, trying to have as many non-zeros to the left as to the right, and then by a horizontal cut where we had to make some compromise. Each split is optimal, but still, you see, we have 128 non-zeros in the blue processor, so that's the most loaded processor, and the yellow processor has a lot less. Also, the black processor only has 30. If we would have our vertical splits done independently, so to the left we would have them higher up and on the right lower down, then we get a much better load balance. And we see that the largest number of non-zeros of a processor is 80 and the smallest number is 76. So that is a good load balance. This is a non-Cartesian distribution, and it turns out that we can get a good low communication volume here as well. So it's not necessarily bad for communication. The picture of the sparse matrix may remind you of the paintings by the Dutch painter Piet Mondriaan. He painted this over a century ago. By the way, Mondriaan, in Dutch you write with a double A, and in English, as he did later in life, with a single A. So there's two spellings, but I chose the Dutch spelling. And this is the composition with red, yellow, blue, and black. And if sometimes the yellow is not very visible in my pictures, it was for artistic reasons that I still included that color and didn't replace them by green, which Piet Mondriaan really didn't like. A p-way matrix partitioning is a division of the matrix into sets, and we look actually at just the sets of non-zeros, so that the union of all sets AS equals A, and that the sets are disjoint and non-empty. The non-emptiness, we won't be very strict in this, but this is if we want to define a p-way partitioning, then otherwise the number p doesn't have a meaning. And we only look at the sets of the indices. So we look at the ij for the non-zeros. That defines the set AS. And we use the notation sometimes instead of v phi, we use the notation for the communication volume v of a0 to ab minus 1. Here we see a matrix, which actually is the matrix prime, as we call it, prime 60. It's a 60 by 60 matrix. I've used it for the cover of the first edition of my book. And this matrix has been split into 4 parts. And the theorem that we have is that the volume of splitting into 4 parts, the volume of the algorithm, equals the volume of splitting into 3 parts, where we just keep blue and yellow still together, plus the volume of splitting that last part into blue and yellow. So this is a property of the communication volume of our parallel sparse matrix vector multiplication. It's not trivial. The proof is relatively easy, but I won't do it here. What does it mean? It means that once I've split the sets, the matrix into a number of sets, and I want to perform another split, I don't need to look at the history of the splitting. I don't need to look at the rest of the matrix. I just need to look at the part that I want to split. And so in this case, the blue and yellow part, they are still together. They still have one color. and I want to split them. So no need to look at how I got here. So that's good. If I do this split, I'm not looking ahead, so I'm not looking at the future. So in this case, we still will have a greedy algorithm. How do we minimize communication? Well, the easiest way would be to paint everything black. But no pain, no gain. We don't get any parallelism that way, so no communication, but communication hurts, but we want some communication. So to prevent this from happening, we need to impose a criterion on the load balance. We could ask that every part AS has a number of non-zeros, nz of AS, which equals the average nz of A divided by P. But that may be too restrictive. A little bit of load imbalance would be allowed. So we have a factor of 1 plus epsilon times this average number. And that will be the allowable imbalance. So epsilon is the parameter that expresses this. So here we consider splitting a matrix, a familiar pi matrix, into two parts. And if we think about it, this matrix has 13 non-zeros. Every non-zero could be either red or blue. So we would have 2 to the power 13 possibilities. And actually we can always, without loss of generality, assign the first non-zero to red. And then we would have 2 to the power 12 possibilities. That's a lot. And trying all of these possibilities, we could only do that for a very limited matrix size. So we need heuristics. We need ways of finding good distributions, hopefully close to the optimal, maybe not optimal. And if we do that, we could try, for example, to split by column, to assign a number of columns to the same processor. At least we don't have then horizontal communication. Or we do that by row. Or we could try both and take the best. That's the Mondriaan approach. And in this case, for such a matrix, we only have 16 possibilities to check. So that is a lot easier. So for a column split, an optimal one would be columns 0, 1, and 2, assigning them to red, and columns 3 and 4, assigning them to blue. You see that we have 4 communications because all rows are split except row 1. Row 1 is red, totally red. But all other rows have blue as well as red. And so we need 4 communications for this. Now, a puzzle for you would be to find an optimal row distribution. Is this one better? This may take a little bit more than the usual 10 seconds. So if you don't want to see the answer, don't want to see the spoiler, just close your eyes. But this is the optimal solution. We have a volume of 3. And you see that column 0 and column 2 do not have any communication. We can repeatedly try splitting by row and column, choosing the best, and do that during our algorithm. And if we have a power of 2, p equals 2 to the power q, then after q levels of split, we are done. So we altogether we need to perform p minus 1 splits. And what do we get then? We get a submatrix, IS with the bar times JS with the bar. And that's a submatrix that we get, and it may have empty rows and columns. If we remove them, we get our familiar index rows IS times JS. So altogether we have our local sparse matrix of processor S, which we call AS. It's contained in a rectangular submatrix, IS times JS, and that one is contained in a little bit bigger submatrix, and these are all disjoint. So that's an advantage of this Mondriaan distribution. We do get disjoint submatrices. This would be the global view. Here we use the Mondriaan partitioner implemented in the Mondriaan software. And this is how the matrix cage looks like. And you also see a distribution of the input and output vectors, not necessarily the same. And we achieve, if we ask for 3% imbalance at most, we achieve that. We get very close to that 2.93% of imbalance. Still quite a bit of communication is generated in this matrix. This is the global view. The global view may be pretty, but you can't see that much about the structure of the matrix. And that's why we also have the local view. This is what the processors see. For example, the black processor has this part. It's a 65 by 45 submatrix. And note that a lot of the rows and columns are empty, which is good because it means that all the non-zeros of that row were contained in the other part. So an empty row and column means avoided communication. Also note that the submatrices with the bars, they exactly fit in the picture, and that's what makes them also similar to a Mondriaan painting. So if we want to do repeated splits, how do we choose our imbalance? If we want to end with 3% imbalance, then we need to cut carefully. For example, if we have 8 processors, you want at every level of split, you want to split with a 1% imbalance in order to, at the end, achieve the 3%. So if the imbalance causes the number of non-zeros locally to grow by a factor of 1 plus delta, and we have each matrix will be then split in 3 levels, or q levels, which is the log of p, then we have a total growth of 1 plus delta to the power q, which we can approximate, or we can approximate it by 1 plus q delta, giving a choice of delta equal epsilon divided by q. So that tells us how to do that. And in the last split, we actually get this approximation becomes exact. We get the exact best split. So we end up with delta. Here's the algorithm that we can formulate based on the ideas that I just explained. So note, we have a matrix A, which we want to split into p parts with an allowed imbalance of epsilon. This is what we do. And if p equals 1, we don't have to do anything. So then, in that case, at the bottom, you see the input matrix just becomes the output matrix. But otherwise, we're going to split the matrix into 2 parts. And we split this by using a bipartitioner. Later I'll talk about how we do that. But we cut the matrix into rows by row or by column. And we use then this delta equal epsilon divided by q. That way we are on track. If the communication volume of these B matrices, which are the output of the bipartitioning, if it's for row, if it is lower than for the column, then we choose those, B0 and B1, as the outputs of this. And then we can split those 2 matrices again, but we adjust the value of the imbalance parameter, because the one that lost, basically got the most non-zeros, has to have a tighter imbalance in the future than the one who gained, gaining in the sense of having the least non-zeros. And so that's why we compute an epsilon 1 and the epsilon 1, the epsilon 0 and the epsilon 1, based on the maximum number of non-zeros that we are allowed to have in the end. And we call this function recursively twice for the part B0 and for the part B1. You may have heard of graphs, but there are also hypergraphs. In a graph, we have vertices, nodes, that are connected each to one other node if all the connections are between two vertices. But here, vertices can be connected in subsets. You can be connected as 3 vertices together, a group of friends. Here we see a hypergraph with 9 vertices, with 6 hyperedges. They are denoted by the ovals. And hyperedges are also called nets, and they are a generalization of the edges of a graph. We've partitioned the hypergraph over 2 processors with 5 red vertices, 4 blue vertices. And you see, for example, on the left, there is a group of 3 that are all, that group is not cut by the partitioning. On the other hand, there's also a group on the top. There's a hyperedge connecting vertex 0 and 5, but 0 is red and the other one is blue. This is what we call a cut hyperedge. And we can use hypergraphs to model the splitting of a sparse matrix. And here we have split by column. We have painted all the columns either red or blue. And the columns, if we transform this into a hypergraph, the columns are the vertices. And the rows express what we want to keep together, if possible. For example, you see that for row 0, this has succeeded because all the non-zeros, they are blue. And they give a net containing 1, 4, and 6. And so altogether we have 6 nets, and we have 7 vertices for this matrix. And the translation gives the exact communication volume. So if a row is split in the matrix, then we have a cut hyperedge, a cut net. This model is called the row net model. So if we want to minimize communication, then what we don't want is like we see for net 1 and 2, so row 1 and 2, they have both the blue and the red vertex, and we don't want that. A method to achieve this is from the 70s by Kearney and Lin. They partition the matrix first by randomly assigning the vertices to processors, and then perform a series of moves. They actually swapped moves, but Fiducia and Matthijses improved the algorithm, and they perform just single moves. So you try to move, for example, in this case, a column to the other side by repainting it into red. Blue goes to red. And then you look what influence this has on the communication volume. And the move that has the best influence, so that lowers the communication volume most, that is carried out. Even a bad move is carried out if this is the best you can do. But then you look at the end, where was the best distribution overall that I got? And this is repeated a number of times. So this works well for for small and medium-sized problems. If we really want to solve big problems, we also do something which is called the multilevel approach. Before partitioning, we make our problem smaller. In this case, I show that by merging columns from the matrix. That also, so we go from the left upper corner, then we go to the right. We coarsen the problem by merging, in this case, each column with its next neighbor. So that halves the number of columns at each step. And we merge the black squares, which are the non-zeros. And then when we have made our problem much smaller, then we can partition. In this case, we only have two columns, so one will be red and the other will be blue. And then we unmerge, which is uncoarsening them. That happens at the bottom from right to left. And each time we uncoarsen, the two columns that we unmerge, they get the same color. If it was red, then the two ones become red. But we can refine the distribution by also trying what would happen if I would instead change one to blue. And that is a refinement. So small adjustments can take place. We could use the Kernion-Lin algorithm for that. And this makes it possible to solve problems with 1 million rows and columns. Much bigger problems you can solve that way. Okay, to summarize, we've seen a recursive algorithm, the Mondriaan algorithm, that gives a p-way matrix partitioning, giving parts AS that are contained in these index sets. We've seen a new notion, hypergraphs, which are a generalization of a graph, which have a set V of vertices, and a set N of nets, which are hyperedges, and they are subsets of the vertex set. And we've seen methods to achieve a good hypergraph partitioning, the Kernion-Lin algorithm, but also the multi-level approach that allows us to scale up. A final question to you. We have seen in the steps of the multi-level algorithm that at the end, we uncoarsen the matrix that you see on the right here, and then refine it, repainting the first column from red to blue. Is this a good or a bad move, considering that the epsilon is 0.2?